Thank you. And this is very exciting for me. This is the first time in a room full of people I've spoken since the pandemic, so it's great to be back to this. So I direct this program, CBA. It was created to study the boundary between digital and physical. I've said computer science was one of the worst things ever to happen to computers or to science, because it's based on unphysical foundations. CBA was developed to study that boundary where digital meets physical. And through the years, we did things like created the first faster than classical quantum computations. We did the microfluidics for genome transplantation to create synthetic life. We were part of the birth of what became Internet of Things. All of those really important fields grew out of asking how bits literally meet atoms. And one of the interesting things was what came out of the people who didn't fit, who came here to work at that boundary. Jason went on, built, and still runs all of Facebook's computers. Rafi built and used to run all of Twitter's computers. One of the things that came out of that was the Open Compute Initiative that blew up the business models of Sun and Cisco by commoditizing computing into simple modular reconfigurable building blocks like you were just hearing about. Max started Formlabs to democratize high-resolution 3D printing. It's now about a $2 billion valuation. Last funding round was about $200 million. Saul was one of the leaders behind the administration's electrification initiative. He did the data for how to electrify the economy. These are some of the remarkable people and companies that came out of asking how bits meet atoms. And what's emerged from that is this scaling. The top 5 points are Gordon Moore's data he plotted for what became known as Moore's Law. He never called it that. He didn't like that name. But he plotted 5 points. Made a really remarkable article where he forecast much of what happened digitally based on those 5 points. The one mistake he made was he said, what if it goes for 10 years? And what I'm showing in the middle on that much longer green line is the 50 years. That's 50 years of mainline Intel scaling. So that was the Moore's Law era. What I'm showing in that red stretch is one measure of the spread of digital fabrication. In this case, it's counting Fab Labs. Excuse me, sorry. And if you look at the Fab Lab spread, for 10 years, it's been spreading exponentially. There's more data than Gordon Moore had when he forecast what became known as Moore's Law. And so one way to view what I want to do now to wrap up is ask, that was 10 years. What if that scales 50 years? What does 50 years of scaling of the performance and spread of digital fabrication look like? It's really the only rational thing to do. There's more data than Gordon Moore had. And a colleague who works with me, Sherry Lassiter, noticed this happening from a pile of papers on her desk that was growing exponentially of requests for Fab Labs. And so this has come to be known as Lass's Law. And so to trace the history, MIT invented computer-controlled manufacturing in 1952. This was when the first time a computer was connected to a milling machine to make parts, early aircraft parts that were too hard to make by hand. Slightly messy history, but interesting history. That was the birth of computerized manufacturing. Very little has changed since then. It might be additive rather than subtractive, but a motion system moves an end effector that deposits or removes material. So at that time, there was one of those on Earth. And that was an offshoot of Project Whirlwind, which was the first real-time computer. At the edge of campus, it filled a building. And all of that added up to make one of these. So from one of those came the mini-computer era. The Whirlwind was transistorized at Lincoln Labs. It was spun off by MIT. It became DEC. DEC created the internet, among other things. That's Kernighan and Ritchie inventing Unix on a PDP. So much of what you do in the phone in your pocket came out of that picture. That's when computing wasn't yet personal, but it was on community scale. So there's on the order of 1,000 cities on Earth. And the analogy to that, I started to appreciate when CBA started. So growing up, I desperately wanted to go to vocational school to learn to weld and fix cars. And I was told, no, you're smart, you can't. And nobody could tell me why. When I worked at Bell Labs, I would go in the workshop and I would get union grievances. And they would say, you have to tell somebody what else, you're smart, you have to tell somebody what to do, you can't do it. And it wasn't until I got here and could get all these machines for myself, I could appreciate this was a mistake made in the Renaissance when the liberal and illiberal arts split. If you want, I can tell you more about that. But CBA started with an NSF proposal to assemble one of every machine to make anything. That's roughly what we proposed. And in the lower levels of this building and the next building, we have tools to make and measure nanostructures, microstructures, mesostructures, and macrostructures. That's the tools we created to start the research I showed you. And then we had a problem. It would take a lifetime of classes to learn to work all those machines. MIT isn't designed to train that. So with colleagues, we started a class modestly called How to Make Almost Anything, aimed at just a few research students to use the tools, and weren't prepared. Hundreds of students showed up desperate to get in the class. It's one of the most oversubscribed classes at MIT. Students year after year say things like, all my life I've been waiting for this. This seems too useful. Are you allowed to teach it at MIT? And have these life-changing experiences. But then the next surprise was what they did. They do semester projects to integrate the skills. Kelly made a device that saves up screams when you're mad and plays them back later. This was a web browser for parrots who have the cognitive ability of a young child and go crazy left home alone. That's an alarm clock you wrestle with to prove that you're awake. Lower right is a dress that you can use to defend your personal space from a creepy guy. These amazing expressive projects with these tools. And that's when I got the students were answering a question I didn't ask. I was asking how to do digital fabrication, how to go from data to a thing. I wasn't asking why. And they were showing the killer app of digital fabrication is personal fabrication. Products not for a mass market, but for a market of one person. And what's very close to home is the whirlwind went from campus to Lincoln Labs, became the TX. TX became the PDP. PDPs created the internet. Route 128 outside Boston was Wang Prime, DEC, Data General, the whole industry. This is Ken Olsen, who founded DEC, who famously said there's no need for a computer in the home. Slightly misinterpreted. He's actually talking about in the home structurally, but he still missed Internet of Things. The whole mini computer industry failed when PCs came. The organizational change lesson is give up. They were all doomed. They saw PCs as toys. But you don't have a computer at home for inventory and payroll. You have all the things that make you, you. And it completely blew up the mini computer industry. And that's what was happening in this class. The students were showing that the killer app of digitizing fabrication is personalizing it in the same way computing was personalized. So around then, Congress passed a rule for big NSF grantees to show social impact. NSF didn't know how to do that, so they turned to grantees like us and said, you show social impact. We didn't know how to do it. A dear colleague, no longer living at MIT, Bell Mitchell, the former dean of architecture, who's responsible for all these wonderful buildings, introduced me to Mel King, grand old man of community activism in Boston, who pioneered bringing community cable into the inner city, then bringing computing into the inner city. And so it was a really next step to say, if there's millions of dollars of tools here, the research is leading up to the Star Trek replicator, can we bring an early version in the field? So we put together something much like a mini computer. Just like a mini computer, this was about 2 tons, $100,000, fills a big room. The picture in your upper left. It includes a 3D printer, but it includes the 9 other tools you need to make useful finished products. So additive and subtractive form and function, programming, circuits, materials, all of that. And that was a fab lab. And the plan was to open one of them, check off this box for community impact, then go back to the lab and go to work. What we weren't prepared for was accidentally starting a global revolution. So in that fab lab, you can make everything in the upper right. Boats, bicycles, furniture, consumer electronics, production tooling. All of that isn't a startup. It's not a business. It's in a fab lab. And we opened one in inner city Boston. There's a strong Ghanaian community that brought one to Sekondi Takoradi on the coast of Ghana. That led to a South African one in Pretoria, then Soshangovi. And then they went exponential. So right now, there's about 2,000 in 150 countries. all compatible, all sharing the same infrastructure. It's as far north as you can go in Europe at the top of Norway, as far south as you can go in South America, the last step before Antarctica in Puerto Williams. We have them in places of sectarian conflict like Northern Ireland. We've had them in war zones like Jalalabad in Afghanistan, and Holland in mixed Arab-Israeli communities. And they flourish in these places, crossing all of those boundaries, driven by the joy and the empowerment of being able to make. So there's thousands of these fab labs. One interesting offshoot is we've worked with a number of companies like Airbus, GE, Dassault Systems, Chevron, on deploying these as part of their corporate social responsibility to invest in communities they work, but also invest in engineers, where Airbus, for example, realized that a kid in a fab lab had better tools to prototype than their own engineers, and so we started helping them create these proto spaces internally as well as externally. So that led to a number of unexpected directions that I never thought I'd be involved in, like city planning. This is Barcelona's mayor, Trias. My counterpart in Barcelona, Vicente Gayart, became the city architect, the planner. He was Gaudi's successor. Barcelona has fabulous design sense, but over 50% youth unemployment. The economy is just broken for a whole generation. So they started deploying fab labs as part of urban infrastructure. So instead of ships with global supply chains bringing in products, and then trash trucks going to trash dumps, they describe that model as PITO, products in, trash out. They want the data to come and go. DITO, data in, data out. The bits come and go, but the atoms stay in the city. So they started deploying fab labs as part of urban infrastructure in the same way the city provides electricity or clean water. It now provides the means to make. And what Mayor Trias is starting is a 40-year countdown to urban self-sufficiency. It's not a step function at the end. The idea is every year a few % more of what's globally sourced is produced sustainably, locally within the city. That's grown into a Fab City initiative. Now about 50 cities of leaders all around the world committing to this direction, not just a smart city, but a fab city of urban self-sufficiency. During the Obama administration, if you know the geometry, this is a mobile fab lab we ran right outside the window of the Oval Office. The White House security was very upset about high-power lasers outside the window of the Oval Office. Obama loved it as an old community activist. And one of the things that came out of that is in the House, Representative Foster, in the Senate, Senators Van Hollen and Murkowski have introduced really interesting legislation for universal access to digital fabrication as a basic human right. We recognize the need for computing and communication. This is now, instead of having a national lab that's $1 billion facility behind guards and fences to sort of bring the labs to the people and make a national network of connected local labs, as a national initiative, really viewing the means to make as a kind of human right. And so this is currently legislation submitted in the House and Senate. And so in light of this meaning, this changes not everything, but almost everything, in that this isn't utopia, it's not free, and I'll talk about the inputs to make things in the labs. But if you go in the lab and make the things I'm showing you, all these assumptions about tariffs and broken supply chains and infrastructure and ports, if you can do this kind of sustainable production locally, a lot of what governments do goes away. You don't need them to do it. On the other hand, you need governments to do a lot of what they don't do, but it doesn't work with hard power, it's soft power, in that in empowering labs, at MIT, we have environmental health and safety that enforces safety rules. There are all kinds of dangerous things you can do in the labs, but you can't have an environmental health and safety department in every one of these. You need to provide incentives to opt in, to work safely, to work reliably, to work in networks as soft power. It changes very much the roles that you need. But one of the core points we've seen is not 100%, but how much is broken in the supply chains, how much of that you can produce locally if you deploy on this very local scale the means of production. And that was really brought home. When the pandemic hit, we were approached by many different groups about using our tools to help with the pandemic response. And what came out of that is a working group I coordinated of hundreds of experts in digital fabrication, material scientists, biologists, but then frontline healthcare workers, regulators, community activists who had never spoken together and worked through a whole sequence of CFD modeling, producing and testing filter media, evaluating PPE and producing it much more efficiently, sterilization. And what was interesting about this effort is there was manufacturing that was slow to ramp up, and then, as you've heard, overshot afterwards. There was do-it-yourself, and there were lots of little versions of just running a 3D printer to make ineffective PPE. In between, there's a lot of research to do it effectively, and then if you use this whole network and coordinate, there was large-scale production in millions of items done by coordinating a network of facilities doing local production. And so it exactly was in between local do-it-yourself and volume mass production. It was relatively high-rate production of distributed local production coordinating this network, really realizing the vision of coordinated distributed production. Any one site didn't have the knowledge to do it, but being in a network did. So to keep scaling, after the PDP came the Altair that was life-changing for people like me. Microsoft and Apple both started on these hobbyist computers. They weren't yet useful, but they were personal. And in that stage, my lab spun off many different companies to make faster, better machines to make things. But these are really, in a sense, disappointing because you still need somebody to design this machine and you need to buy it. What's much more exciting is the machines making the machines. And to the questions just come in, I'm going to be talking through the sequence of finer and finer resolving what you can make. So these are all rapid prototyping machines made on the rapid prototyping machines. So it's machines making machines. And so instead of going to a fab lab to get access to the tools, you go to a fab lab to get access to the tools to make a fab lab. And the goal is for the machine to be as expressive as the project on the machine. Rather than them all being the same, you can adapt the machine to the application. This is really kind of personal robotics doing rapid construction of this machine building. And we're very quickly pivoting to deploying fab labs this way. And what's driving that is to make the costs go down, we're spending more money. With a number of sites in the world, we're helping them set up million-dollar super labs, a bit like the CBA tools here, designed to make not just fab labs, but parts of the machines. This is the first one in Kerala, south of India, which has very adventurous leadership. Next one we're doing is in Bhutan. You may know Bhutan, its economy is based on gross national happiness. It doesn't mean everybody's happy, but it means they measure health, stress, education, well-being as the output of the economy. And the G&H office, the Gross National Happiness Office, is feared. Because the G&H office is like the IRS there. Everybody is accountable to measures of well-being, and you have to report on how you're improving well-being. So this remarkable country, but they're stuck buying crap trucked in from China, India, or Japan. And so we're deploying we first did fab labs in Bhutan. We're now doing a super fab lab to deploy this throughout the country to bring the Buddhist mindset inside the heads out to manifest it physically, to give them the means to create what they consume there with the idea of labs making labs. A colleague in Detroit doing this, Blair Evans, explicitly, and he's right now reconstructing Idlewild, if you know what that is, in northern Michigan, explicitly runs it where a third of the time in the lab is for traditional economic activity. A third is economic but post-money, barter, exchange, other carriers of value. And a third is for the good of the community but not economic activity, creative expression, well-being of the community. Really starting to tease apart, we have a litany of jobs equals work equals money equals consumption. That's a fairly recent model. And again, if you have the means to make, it's not utopia, it's not free, but you can disentangle all of those things. And rather than just trying to create jobs and economy, you can create well-being, the outputs of the economy, by providing access to these sort of tools. And so in the Fab City project, examples include aquaponics and hydroponics to grow food, rapid prototyping of shelter on the scale of the built environment, making transportation systems, making urban data networks. And one of the interesting things happening also is reversing urbanization, that one of our favorite fab labs is in a very remote site in Western Maharashtra in an isolated village, and people come from Mumbai or Delhi to get away from the pollution and the crowds and the noise in the city. It has all the machines and global connectivity and then fresh air and space and reversing urbanization. So to keep scaling, after personal computers came now on billions is PCs for everyone. And there's a problem. What you can't read at the top of the slide is the inventory in a fab lab. You get the machines, but then these are all the supplies that go into it. Below that is just part of the electronics inventory. To make all of the things I'm describing, you have to put intelligence into it, which means making electronics. In the lab, we make PCBs and do surface mount rework and embedded programming, but we're not making the electronic components. And so you need all of, to source all of these things. Here, the inspiration is biology. On the right is your inventory. You're made from 20 parts, the 20 primary amino acids. The amino acids are, what's remarkable is they're not remarkable. They're hydrophobic or hydrophilic, they're basic or acidic, they just have typical properties. And you can compose them. I'm showing the muscles that make me move, what I use to smell, what I use to think. All of that molecular machinery comes from composing 20 parts. And the way it's done uses everything Shannon and von Neumann and Turing taught us about coding and computing. So you can program that. This is work out of my lab on coding in molecular biology. You can program that, but you're limited to biomaterials. And so I've been very interested in an analogy. In biology, there's a hierarchy from a primary coding sequence to a secondary geometrical motifs to tertiary functional units like electron donors or acceptors to quaternary machinery like a ribosome. And in that hierarchy, what's interesting is the code doesn't describe the thing. The code actually becomes the thing. And in it, you can do all the things we do in digital things. We can detect and correct errors. And so we've been looking at how to build primary, secondary, tertiary, quaternary structures by coding the construction. Everything I just said also applies to Lego. Lego lets you detect and correct errors. It's reversible. It's hierarchical. It has all of those properties. We're looking at building by not printing or cutting, which dates back a long way, but by assembling and disassembling. So we're working with companies in the electronics industry. DigiKey sells hundreds of thousands of types of resistors or capacitors or inductors just for the discretes. In terms of material properties, those really just have three: conducting, insulating, resistive. And so I've described to the electronic industry, I can make all of their hundreds of thousands of SKUs with an inventory of 3 parts. And what I'm showing is scaling micro Lego and then making assemblers of these very simple properties you can then compose to span the space of all of these materials. And so the machine on the left is a cross between a pick and place and a 3D printer to place volumes of these functional materials. On somewhat larger scales, these assemblers, once you digitize the structure in the way I'm describing, you can view the assembler and the material as a joint material robot system, and the assembler can become small compared to what it's building. And so we showed by linking loops of carbon fiber, we set the world record for the highest modulus ultralight materials. We showed that by making a few part types, we can span a range of mechanical metamaterials. This is, on the right is NASA Langley's biggest wind tunnel. This is, we made a morphing aero structure, a long-standing aero goal, where instead of putting mechanisms into it, which has been a long-standing challenge, we made sort of the whole structure into a mechanism by deforming these cellular structures. We've been working with the auto industry to make cars, shipping companies to make boats, NASA in space. And the goal of all of these is supply chain. So it's getting rid of belugas and dream lifters and these globe-spanning supply chains to make the parts, and just having feedstocks of these simple building blocks with these swarms of these automated assemblers to do now state-of-the-art fabrication of high-performance structures, a very different approach to it. So finally now, After PCs came the Internet of Things era of trillions of devices. And here there's a problem. Again, I'm plotting resolvable elements versus elements per second. The red points are state-of-the-art manufacturing. The green parts of state-of-the-art additive printing. And then orders of magnitude away is biology. Orders of magnitude for biology's capacity to place resolvable elements. And what's going on there is an invention that's 4 billion years old. That's the age of the ribosome. And key to it is ribosomes are slow. They turn messenger RNA into a protein about 1 amino acid a second. They do all the things a good coding system does in detecting and correcting errors. But they're slow. They do it at about 1 hertz. But ribosomes make ribosomes. So because ribosomes make ribosomes, they exponentially ring up. So a cell can have trillions of ribosomes. And that's what gives you this enormous capacity. And so that's why really the core project in my lab is that recursion of assembling assemblers. And so we're working on assemblers that assemble assemblers from the parts they're assembling. And that's the heart of the whole story. There's no analog in manufacturing. You've heard today about all of the issues about demand versus supply. There's no in biology, you can ring up exponentially a bioreactor, and you can ring it down when you don't need it. There's no manufacturing analog until you get this recursion of recursive self-assembly. And that's why we're so focused on making an assembler that can assemble an assembler. And so to do that, this is just a map. We have to redo just about everything. So upper left, we've been working with DARPA and CAD and CAM companies on design. Once you're making this exponential complexity, the design tools break. And so in biology, your genome doesn't store the fact that you have 5 fingers anywhere. What it stores is a developmental program in one of the oldest parts of the genome that encodes things like symmetry breaking and gradients. And at the end of that, you get 5 fingers. And part of that is compression, but the main part of it is most changes to the genome are fatal or inconsequential, but not interesting. It's hard to innovate. Right at the heart of machine learning is representation. So developmental programs are a representation for search. Today, when you design a product, you design it. Here, what we're doing is designing over developmental programs to sort of embody machine learning in design. Then that breaks the simulation tools. We've been working with DARPA and NASA on redoing the foundation of multiphysics modeling. In this world of exponential feedback, you can't really standardize. We've been working with NIST and DOE on how machines can adaptively learn to model the materials they're processing rather than feeding it forward. Once you can do this sort of construction, you can build intelligence. We're working with DARPA and AFRL. There's a kind of a firewall between the design algorithm in a computer and the construction of the computer. We're working to make computers where you can code the construction of the computer, where you can match the construction of the computer with the problems it's solving. This is all part of building the stack for a world of exponential manufacturing. So to start wrapping up, to look at the numbers, we're living in an AI revolution, except it not really isn't, in that it's just been steady scaling. Supercomputers now do 10 to the 17 ops per second. Your brain does on the order of 10 to the 17 ops per second. We just caught up to the complexity of a brain, and we'd be remiss if it didn't work. But if you look at the exaflops and the petabytes, the fab making the supercomputer is doing on the order of 10 to the 10 resolvable elements per second. You digesting the snack and the break are doing 10 to the 18. You're 8 orders of magnitude ahead of the state-of-the-art chip fab. That's this gap in fabricational complexity. Now, that's not new. Von Neumann and Turing are well known for the foundations of computing. What history has largely forgotten is they didn't believe in digital separate from physical. Von Neumann ended his life studying self-reproducing automata, how a computer communicates its own construction. Turing ended his life studying morphogenesis, how genes give rise to form, exactly the things I've been talking about. They ended their life studying that as the heart of computing, is how it becomes physical. In a computer science education, you won't learn about any of this, but this profound connection between communication, computation, and fabrication is where they ended. At the time, that was theoretical. It's now experimental, and we can do it with these remarkable implications. One more way you can understand this is, this was a fun program I did that's bonus material for the movie The Martian. It's how to go to Mars without luggage, how to bootstrap a civilization. What's called ISRU, in situ resource utilization, assumes you need 500,000 types of resistors. You need to redo the Industrial Revolution. And what we're realizing is the minimum building blocks for a civilization are maybe 20 parts, these 20 properties. But they're like amino acids, but for inorganic systems. And to wrap up, my most recent book I wrote with my younger brother, Alan, who led the biggest video game studio at Activision, my older brother, Joel, who ran the National Labor Relations Organization. After I talk about the things I spoke about, audience would clap and say, that's exciting. And if you listened, you'd hear them groaning. And they're groaning because the theme today is disrupt. If you looked at the original disruption of digital computing and computation, the wonderful visions, sort of libertarian flavored at the beginning, the other thing Gordon Moore didn't anticipate is spam, fake news, income inequality, all the things that have gone wrong in the digital era. The reason Joel and Alan were groaning is they believe me for the technology, but they think I'm being naive. If anybody can make anything, we're done. You also need literacy, you need access, you need to shape the evolution of it. And so this book was an exercise to look at, if we're not 50 years at the end of a Moore's law, but now Lass's law, but if we're at the beginning, how do we shape the revolution for it to be inclusive and responsive? And as I hope I've shown, it really requires revisiting just about all of the assumptions about how an economy functions, how technology works, how society works, once you provide the means to go from digital to physical and physical to digital. And so with that, I'll thank you, and if there's time, just take a couple questions. Let's see, how might personal printing affect city development? That one is just spot on. Go to fab.city, and cities assume today global supply chain for them. This transition from pedo to dido, products in, trash out, to data in, data out, is going very quickly with all the cities signing up to really produce food, shelter, data, all of the things. That's very clear for city development. What can't you make in the Fab Lab? In a Fab Lab today, you can really make just about anything. So Fab Labs make all the products I showed you. Fab Labs make biolabs to do biotechnology. What they can't make is what goes in them. So in the stages I showed you of 10 to the 3, 6, 9, 12, a Fab Lab can make just about anything, but it needs a chip fab to make the integrated circuits. One step in is the microassemblers to get rid of PCBs and connectors, but we still need the chip fab for what's inside the chip. And eventually, the microassemblers, we're really looking to do things like chip fab in a tabletop process through microassembly. And so it's not what you can't make. It's that it's sort of cutting out more and more of the supply chains you need to live on. Future minds. Yeah, for me, again, what I alluded to is, depending on how you count, we're in the 5th boom-bust cycle of AI. There was first computers, there were expert systems, there were perceptrons. There have been about 5 of these boom-bust cycles. But if you do a different thing, which is not plot boom and bust of AI work, but just plot ops per second, bits you can store, these basic parameters, it's just been steady progress. And so the real revolution in AI has been this steady progress where the computing is about the complexity of our brain, but we now have this gap in the physical complexity. I think what's going to be so interesting is this transition from designing something, colleagues from Autodesk here, where you design something with a tool, to a collaboration where you describe what you want. And so it's not imperative you say what to do, but it's declarative. You say what you want to do, and you collaborate with the tool to figure out how to solve the problem. And we found you need deep hybrids between people and machines, and it's very much about embodying AI in the systems, and we're moving towards going from offline to online. And so this is really about embodying artificial intelligence. CAD classes, one of the fun things is, along with the oversubscribed class here, I teach a global version of this through the Fab Lab network. And it's training a new generation of designers. There really isn't a word for that. I alluded to the mistake in the Renaissance when the liberal and the liberal arts were separated. What the skills here are design, but they're design in hardware and software and form and function. It's not a team of one of each of those skills. It's new means of expression that have changed since the trivium and the quadrivium. And so it's really a new kind of curriculum in this means of design. Code in the material, and then I'll end with the trend. The code in the material is exactly what I described in the developmental program gives a coding sequence that actually becomes the thing. And so in the stages I showed you, to start, we just have machines, computers controlling machines. We're then getting rid of traditional machine interfaces to make that connection deeper. But then moving towards in this world of assemblers where you can't separate the assembler from the materials they're assembling and they merge. And then I'll end with, I'm not forecasting, I'm making bold predictions about the present. What I've shown you is a decade of exponential scaling that's more data than Gordon Moore had when he made his forecasts. There's no sign of that exponential scaling slowing off. Technologically, everything is humming along. I'd say the hardest thing, and then the opportunity and the challenge is, we're working with a number of big companies who are going to be here in 50 years on how it changes their business. There are a lot of mid-sized companies that think these are toys and they're going to be destroyed, like Wang and Prime and Deck in general. And then we're working on a lot of groups of creating not just new businesses, but new ways for economies to function. And so thinking about how do you live, learn, work, and play, if anybody can make anything anywhere, is the homework assignment I'll leave you all with. Thank you.